Good evening, dear students. Today we are going to speak about the continuity of electrostatics. Already you had a discussion about the electric charges, electric fields, and then the electric field due to an electric dipole, and field along the axial line of an electric dipole. Now we are going to speak about the electric field at any point along the equatorial line of the electric dipole or the equatorial plane of the electric dipole. As you know, the definition for electric dipole is the product of any one of the charge and distance of separation between the two charges. As a charge produces electric field around it, an electric dipole will also produce electric field around it. The nature of the electric field is quite different from the field produced by point charges. The field produced by point charges is, if it is a unit positive charge or simply a positive source charge, the field lines acts outwards, and if it is a negative charge, then the field lines will act towards the negative source charge. This is how the field lines will be present. If suppose we consider a dipole plus q and minus q, as you know very well, the lines of force start from positive charge to negative charge. So the field lines whose presence can be studied with the help of test charges. So field line will be of this form. Field line will act along these directions. This is how the electric field line will be. This is a dipole. Two equal and opposite charges separated by a very small distance constitute an electric dipole. This is an electric dipole. Even a point dipole is there, which we are going to use in our further discussions. So in order to understand what is a point dipole, we can have a simple idea that if the two charges are tending to approach each other and they are going to approach a zero distance, and the charges whose magnitude approaches infinity, then the two charges which are kept separated by a very infinitesimally small distance is said to be a point dipole. We can see here the point dipole has its presence plus q as well as minus q like this. Both are associated very close. It appears to be like a single point charge. It's supposed to be a single point charge with which we can define the presence of electric field very clearly. It starts from plus q to minus q. It starts from plus q to minus q. The field lines will act like this. So explaining electric field around a point dipole is quite easy when compared to the explanation given out for the electric fields around a point charge, which has somewhat greater separation when compared to a point dipole. This is how a point dipole will exist. The electric field due to a dipole along the equatorial line now. Let us consider an electric dipole minus q and plus q, which are placed at A and B. For our understanding, we are showing it at a far off distance, but actually by definition they are at a very close distance, infinitesimal separation, but we are considering it at some distance for our understanding to have a clear picture about the electric dipole. They are separated by distance 2a, which can be referred to as A and A. The dipole moment acts from minus q to plus q, minus q to plus q. We are going to, or let us say O be the midpoint of the dipole. We are going to calculate the electric field at the point C, which is at a distance r from the midpoint O of the dipole, which is nothing but the perpendicular bisector of the electric dipole. If you draw a plane enclosing this line, then this plane is called the equatorial plane. Equatorial plane. In this plane, we are going to calculate the electric field. At the point C, the electric field due to the charge plus q will act along BC. I can represent this as E plus vector, and at the same point C, the electric field due to the charge minus q is said to be E minus vector. As you know, the definition of electric field at any point Electric field at any point is defined as the force experienced by a unit positive charge placed at that point. If I place a unit positive charge at this point, plus Q charge will repel this unit positive charge, so the force will act on this unit positive charge outwards. So electric field line will act in the outward direction, so along BC, and the same unit positive charge will be attracted by minus Q charge, so that the electric field will be attracted towards the negative charge. So the electric field line will act along the direction of attractive force, so E minus vector. The magnitudes of the electric fields E plus vector and E minus vector are the same because they are produced by the same magnitude of charges, Q and Q. Nature of charges, one is plus Q and another one is minus Q, but magnitude of charges are the same. So the electric fields produced by the two charges at the point C is the same. So E plus and E minus, whose magnitudes are same. So I can write the magnitudes of E plus vector and E minus vector are equal. E minus vector are equal. So this is about the field produced by this dipole at the point C, about its magnitude. What about the direction of electric field at the point C? The direction of electric field, as I have mentioned, one is acting along BC and another one is acting along CA. So two fields are acting at different directions. If theta is the angle made by the line joining the 2 points BC and AC respectively, then we can say here the electric field at the point C, whose resultant direction can be obtained by taking or by resolving the components of these electric fields, E plus vector and E minus vector, which are making angle theta with respect to the horizontal. So if this is the angle theta made here, then I can say here theta is the angle made by these electric fields with respect to the horizontal. So this will give you the resultant electric field or total electric field. Resultant electric field or total electric field. So resultant electric field will be acting in a direction opposite to the direction of dipole moment P vector, or else I can say it will act in the direction of minus P vector. It acts along the direction of minus P vector. So by two ways we can express here. E vector acts opposite to P vector, or E vector acts along minus P vector. E vector, resultant electric field E vector acts along minus P vector. This is the resultant electric field. How will you get this resultant electric field? By resolving these two electric field vectors, E plus vector and E minus vector. How will you resolve this electric field vector? If vector is making an angle theta with respect to the horizontal, to the axis with which the field is making an angle theta is said to be the cos component. So I can take this as E plus cos theta or E plus vector cos theta, and the vertical component is E plus vector sin theta. Similarly, for E minus vector, the electric field is E minus vector cos theta, and the perpendicular component is E minus vector sin theta. Here in this resolution of vectors, the components E plus vector sin theta and E minus vector sin theta are equal in magnitude and acting in the opposite directions, so they tend to cancel out their effects. So the role of E plus vector sin theta and E minus vector sin theta is nil in this particular case. So the resultant electric field at the point C is provided only by the two electric fields E plus vector cos theta, E minus vector cos theta, which are acting parallel. So I can say the resultant electric field at the point C is due to the parallel components of the two electric fields E plus vector and E minus vector. If you calculate, or if you want to calculate the resultant electric field at this point, I can give out the expression for the resultant electric field or total electric field. E total vector is equal to E plus vector cos theta into P cap, as P vector is acting in the direction opposite to that of the original dipole moment direction. I can say the total electric field is acting opposite to the dipole moment. So I can introduce a negative sign here as we are dealing with vectors. As we are dealing with vectors, E total vector is negative of P vector plus of minus modulus of E minus vector cos of P cap. So if you look at this expression, this plus of minus can be changed as minus itself. So the total electric field at the point C is the sum of the two parallel components E plus vector cos theta and E minus vector cos theta. I have taken the modulus of E plus vector and modulus of E minus vector, and the introduction of negative sign in this particular expression is due to the opposite direction of action of opposite direction of electric field with respect to the dipole moment. Here the magnitudes of the E plus vector and E minus vector is the same, which is q divided by 4 pi epsilon naught r square. As we saw earlier in the expressions, the electric field due to a point charge at any particular point, distance r, can be given by the expression q by 4 pi epsilon naught r square. This is the electric field, magnitude of electric field. Magnitudes of electric fields due to plus q charge and minus q charge has the same value, q by 4 pi epsilon naught r square. Here it is a general expression, but the distance r, which I have represented here in this particular expression, is not r itself. If you look at the diagram, the value of r is different. I can express it as q divided by 4 pi epsilon naught r square plus a square by Pythagoras theorem, because this distance r is nothing but the distance of the point C from point B as well as the distance of point C from point A. So if we need this distance, what we have to do is, this side, on the two sides of a right angle triangle is r and a, and the hypotenuse is this one. Hypotenuse square is the sum of the squares of the other two sides. So what you will have is square root of r square plus a square. This will give you the value of hypotenuse by Pythagoras theorem. As I have taken it in terms of square r square, I expressed it as r square plus a square. So the magnitude of electric fields due to plus q charge and minus q charge is q divided by 4 pi epsilon naught r square plus a square. On substituting this value in this expression, let us consider this as 1 and this as 2. Substituting 2 in 1, I can get the total electric field expression as minus of q divided by 4 pi epsilon naught r square plus a square, as the magnitudes are same and they are existing twice. So I can write 2q by 4 pi epsilon naught r square a square into cos of theta into p cap. Cos of theta into p cap. We need to know the value of cos theta. You consider this right angular triangle. I can take any right angular triangle. I am taking the right angular triangle COB. This is theta, this is r, this is a, and this is square root of r square plus a square. If I need cos theta from this right angle triangle, I can write cos of theta is adjacent side divided by hypotenuse, which is a divided by square root of r square plus a square. In this right angle triangle, this a is the adjacent side, square root of r square plus a square is hypotenuse, so cos theta equals a divided by square root of r square plus a square. So the total electric field now can be expressed as E total vector is equal to minus of 2q. Instead of cos theta, it is a divided by r square plus a square the whole power 1 by 2. So I can write 2q a divided by 4 pi epsilon naught r square plus a square the whole power 3 by 2 into p cap. We can write, since cos theta equals a divided by square root of r square plus a square. So how this manipulation has been done? Already we had 2q divided by 4 pi epsilon naught r square plus a square alone, and in the position of a divided by r square plus a square the whole power 1 by 2 we had cos theta. As you know very well, x into x power 1 by 2 is x power 3 by 2. That's how I have taken this as r square plus a square the whole power 3 by 2 into p cap. And this expression E total vector is equal to minus of P vector divided by 4 pi epsilon naught r square plus a square the whole power 3 by 2. Since P cap is equal to, or P cap into 2a into q is equal to P vector, which is nothing but the definition for unit vector. Unit vector is a vector divided by its own magnitude, P vector. Magnitude of dipole moment is 2a into q. So instead of 2a into q, I can write modulus of P vector. Modulus of P vector is taken as 2a into q. Multiplied by unit vector will give you the vector. So 2aq is nothing but the magnitude modulus of P vector multiplied by P cap will give you P vector. So minus of P vector divided by 4 pi epsilon naught r square plus a square the whole power 3 by 2. If the distance r to the point C from the midpoint O of the dipole is much greater when compared to the separation between the two charges, if r is much greater than a, then I can neglect a square. A square can be neglected. A square can be neglected from this expression. I can write this expression as expression 4. From 4 I can neglect a square. So the total electric field E total is equal to minus of P vector divided by 4 pi epsilon naught into r square the whole power 3 by 2. This gets cancels out. So minus of P vector divided by 4 pi epsilon naught r cube. So the total electric field along the equatorial line or in an equatorial plane is given by this expression. E total is equal to minus of P vector divided by 4 pi epsilon naught r cube. And this is for the condition r much greater than a. If the distance of the point C from the midpoint of the dipole is much greater than the separation between the dipoles, then I can get this expression E total vector equals minus of P vector divided by 4 pi epsilon naught r cube. If you recall this expression and compare it with the expression what we have obtained for the field at any point along the axial line, then we can write this is for equatorial line, this is for equatorial line, and for axial line, electric field at any point on the axial line, it is minus of, or it is 2p vector divided by 4 pi epsilon naught r cube. If you look at the case here, in this particular case, the electric field vector acts along the direction of dipole moment, and in the case of equatorial position, electric field vector acts in a direction opposite to that of the dipole moment. So there is a marking difference between these two. The field along the axial line is 2p vector by 4 pi epsilon naught r cube, and along the equatorial line it is minus of p vector by 4 pi epsilon naught r cube. On comparing these two expressions, we can bring out some important inferences. What are they? We shall list out one by one. 1. If you look at the expression for the field along the axial line, it is 2p vector divided by 4 pi epsilon naught r cube. And for equatorial line, it is minus of p vector divided by 4 pi epsilon naught r cube. When you compare the magnitudes of these two, I can say the field along the axial line is twice the electric field along the equatorial line. So from this we can write the ratio of field along the axial line to that of the equatorial line is 2:1. If they ask you the ratio of field along the equatorial line to that of the axial line, it is 1:2. You can change the ratios here. And also, if you look at the expressions, this electric field vector along the axial line is positive, whereas electric field vector along the equatorial line is expressed in negative sign, which means that electric field vector acts along the direction of dipole moment in the axial line. Electric field at any point on the equatorial line or equatorial plane is acting in a direction opposite to the direction of dipole moment. So we can say here the field angle between the field, electric field along the axial line and the dipole moment p vector is 0 because they are acting along the same direction. Similarly, the angle between the electric field at any point on the equatorial line and the dipole moment is 180 degree because they are acting in a direction opposite to each other. This is the first inference what we have made. Second one, if you look at the case of the field due to a point charge and the field due to an electric dipole. The electric field due to a point charge is given by the expression Q divided by 4 pi epsilon naught r square. So I am writing the magnitude alone. So electric field due to a point charge is inversely proportional to r square, whereas the electric field due to a dipole varies inversely as either for axial line or for equatorial line, whatever, 2p by 4 pi epsilon naught r cube or minus p by 4 pi epsilon naught r cube. Here I can write the field due to a dipole varies inversely with r cube. So the field due to a point charge varies inversely with r square, field due to a dipole varies inversely with r cube. So around the charge distribution, the electric field will become 0 very soon as you move away from the dipole. At very smaller distances itself, the electric field due to the dipole will become 0, because E varies inversely with r cube. Electric field varies inversely with the distance cube, whereas the field due to a point charge varies inversely with r square. So the existence of the electric field due to a point charge will be further away when compared to the field produced by an electric dipole. So what we can conclude is that, or why it happens is that, we can say the electric field at any point due to a dipole happens to become 0, or I can say here plus q and minus q are considered. I am assuming the point over here, they are separated by a small distance. At this point the electric field will become 0, whereas the field due to a test point charge at the same point will not become 0. It will be still existing, or it will still proceed further, but the field due to the dipole will become 0 at some point distance r. So why does it happen? As you move away from the dipole, what happens is that at far off distances these charges tend to approach. It tends to approach. It appears to come close to each other and neutralize each other. Plus q and minus q will get neutralize each other. If the charges tend to neutralize each other, then they will not result in any electric field at far off distances. So the electric field will go on decreasing as the distance increases. That is inferred by these expressions. Field due to a point charge as well as field due to a dipole varies inversely with the distance. But the variation takes place as r square in a point charge and r cube in a dipole. So what happens is that the field vanishes faster in case of a dipole when compared to the field due to a point charge. So at far off distances, as the same distance r is considered for a point charge, the electric field will not be 0. It will be still existing at that point, but electric field due to a dipole will become 0. Why it happens? Because as you move away, the two charges tend to approach close to each other and they appear to neutralize each other. Because of that, the field will become 0. This is very, very simple. If you look at the sky, the stars appear to be very close to each other, but exactly they are not. The two stars are at far off distances. They are light year distance apart, but they appear to be very close to each other. Why? It is because when we observe from the surface of Earth onto the sky, the two stars at a far off distance from us, so the distance between the observer and the stars matters here. This distance is very large. When compared to this distance, the distance between the two stars is much closer. They appear to be very close to each other. In the same way, if you move away from the electric dipole, at a far off point, we can say the two charges come close to each other and they neutralize each other, so they won't result in electric field at farther distances. So very soon they will run out. The field due to the dipole will not be existing. So the presence of electric field around the electric dipole can be easily expressed here. It starts from positive charge and terminates at negative charge. As you know it very well, the field along the axial line is 2p by 4 pi epsilon naught r cube. So the field lines whose magnitude is greater along the axial line. As you move towards the equatorial position, the field whose magnitude decreases. So if you are asked to explain where the magnitude or the field strength is more, we can simply say field strength is more at the axial line and field strength is less at the equatorial line. So if you draw the diagram, you can have a clear picture here. If you consider a point P which is at a distance r over here, the field line will start from positive charge and terminate at negative charge. If you look at the case, the field acts in a direction like this. This is the direction of electric field, and another field line will be acting along this direction. Dipole moment will act from minus q to plus q. So just look at the case here. The same diagram what we discussed, for that we are determining the electric fields here. The electric field acts opposite to the direction of dipole moment in this particular case. Along the axial line, we can just calculate here simply. The electric field will act in the direction of the dipole moment. Here the electric field along the equatorial plane acts opposite to the direction of dipole moment, right? And third inference is that the expressions Ea equals 2p vector by 4 pi epsilon naught r cube and E vector equals minus p vector by 4 pi epsilon naught r cube, both the expressions for axial field along the axial and field along the equatorial line, they are applicable only when the condition exists if r is much greater than E. These expressions are for this particular condition for r much greater than E. If suppose I bring out a condition that if the distance of separation between the two charges 2a tends to become 0, it approaches 0, and the charge approaches infinity, then the product of these two, charge into distance of separation, which is nothing but the dipole moment, is finite. Then we can say this dipole is a point dipole. This dipole is a point dipole. This dipole is a point dipole. So which one is a point dipole? If the separation between the two charges tend to approach 0. What is the meaning for approaching 0? It's simple. It is the next, or it is the step ahead, a step before the two charges are at. If the charges move further, then the distance of separation will become 0. So we can say the 2a approaches 0 here refers to this plus q and minus q are separated by this distance 2a. They are brought close to each other. At this point, they are separated apart. If they are moved further, then they will be neutralizing each other. This is the point where we have to say 2a approaches 0 and q approaches infinity. One thing you have to be very clear. Infinity, in case of mathematics, when we speak about mathematics, they do not have any finite limits. That is different. Here, in case of electrostatics or in microscopic world, infinity has a different meaning. We can simply say if the dimensions are, or if the distances are large when compared to the separation between the charges, then this distance r is considered to be infinity. Simply to say, if the two charges are kept separated by a distance of micrometers, then even 1 meter distance, even a centimeter distance is infinity. Even a centimeter distance is infinity when compared to 1 micrometer. So we can simply say if a positive charge plus q is considered, around the positive charge field lines will exist. At this particular point, we can say the electric field vanishes. So this point can be considered as infinity. Which one is this? If you consider the same plus q charge as the central charge of a atom, which we call a nucleus, then the nucleus will produce a positive field around it, and that field whose existence will become 0 at a particular point, which we used to call the boundary of the atom. So boundary of what is the dimension of an atom? 10 power minus 10 meter. So even a 10 power minus 10 meter distance is considered to be infinity. So infinity should not be confused when you think of in case of, as you think of in the case of mathematics. That is different. That infinity has no finite limits. But here this infinity is considered when the distance of separations are brought into play. If 2a is much smaller, then we can say the dimensions of charges are infinity. This distance r is very large, even you can say it is at infinity. So conditions depends. So this dipole is acting as a point dipole. For a point dipole, these two expressions, Ea equals 2p vector by 4 pi epsilon naught r cube, E vector equals minus p vector by 4 pi epsilon naught r cube, is valid for any distances, which means if you consider close to the dipole or at a far off distance, whatever it is, these two expressions are valid. But that is only for point dipole. If you consider an ordinary dipole which is of a finite separation, then for them the two expressions are valid only for this condition, r greater than or much greater than a, or much greater than a. This expression is valid only for r much greater than a in case of ordinary dipoles. If you consider point dipoles, these expressions are valid for any distances, whether the point is assumed close to the dipole or at a far off distance from the dipole, doesn't matter.